Hi, this is Alex Georgescu. Thank you for joining my talk, and I'll be talking about trigonal symmetry and its electronic effects in two-dimensional dihalides and trihalides. And this work is already on arXiv, where you can read about it in more detail. So to start with, I'll actually start with a transition metal atom in the vacuum. So this M atom here, it will have its d orbitals degenerate, so they'll have the same energy. If you put it in a cubic environment, this degeneracy is broken and you'll have a 2-3 set of degenerate orbitals, the EGs and T2Gs. Break the symmetry further using a Jahn-Tiller distortion, you will have 1, 1, 1, 2 degeneracy. And this Jahn-Tiller distortion is characterized by the metal ligand bonds being inequivalent. So they look, for example, like this L2 and the L1s in plane, which leads to this additional crystal field splitting. So you can think of this L2 over L1 determining this crystal field splitting here. And this is quite important in materials like copper at high temperature superconductors, for example, where you really want a strong orbital polarization. But there are other ways to distort octahedron away from a cubic environment. So for example, you can distort along the 1, 1, 1 direction, as I'm showing here. So to better understand this, we rotate the octahedron such that the 1, 1, 1 direction points up. And we pull on the ligands, as shown here. So the interesting thing here is that the metal ligand bonds are still equivalent after this distortion, but the ligand-ligand bonds are not. So you now have this L1 and this L2, which leads to this 2, 1, 2 splitting of the orbitals. And the trigonal symmetry is maintained by the fact that you still have a threefold rotation as a valid symmetry operation. The orbitals that we are left with also have different functional forms. So while the EGs actually look the same as before, the T2Gs are different. So we have this A1G and EG pair. Okay, so going back to this, again, this is characterized by ligand-ligand bond length differences. And this is also true, for example, for hexagonal perovskites, for example. And while the Jahn-Tiller distortions we're more used to in oxide physics are characterized by metal ligand bond length differences. So if we look at the 2D halides and their symmetry breaking, if you start with an octahedron in the vacuum, which has an OH symmetry group, the moment you put this into a monolayer, you reduce the symmetry to trigonal. Slightly different symmetry depending on the dihalide or trihalide type material you're looking at. So what I mean by that is if you look at the dihalides and trihalides here, the dihalides have a triangular lattice for the transition metal sites. The trihalides have a hexagonal one. And the octahedra are a little bit different as well. So on one side, you have these L1 bonds parallel to the plane. And then you have the L2 for the dihalides and the trihalides that connect the octahedra and are not parallel to the plane, and these L3s, which do not connect octahedra. But regardless, you have threefold symmetry in both cases that is maintained. So you still end up having the same orbital representation in both cases. Okay, so we can also break symmetry further with layering and other possible modes that I'll get into a little bit later. But to give you an example, titanium chloride, do a calculation with DFT, no U, non-magnetic. We just want to see the crystal field splitting as a result of distortions. You take the material, you distort it, and one of the things you see, again, as a function of L2 over L1, is that you can control the crystal field splitting. And importantly, you control both the band energies as well as the orbital occupancy differences between the lower orbitals. We note that they're never degenerate. So what I mean by that is the L2 over L1, where these intersect, the energies and the occupancies intersect are different, which is because the symmetry breaking is intrinsic to the layered structure. It is never cubic. You do not have threefold degeneracy of the lower three orbitals. Hopping is suppressed along Z. The interlayer distances are key to the crystal field splitting as well, as you can see here. And they become asymptotic. The crystal field splitting becomes asymptotic for large interlayer distances. So again, ligand-ligand bond lengths and interlayer distances can control a splitting between these orbitals. So the effect of correlations in magnetism is to amplify everything I've been showing you. So you take this material, do a DFT plus U calculation, small-ish U, ferromagnetic because you have a single unit cell, and you have a strongly orbitally and magnetically ordered state as a result, with the EGs, lower EG half-filled and fully magnetically polarized. So the bands actually look like this. And so this is in the absence of spin-orbit coupling, of course. So the bands look like this. So you have these EG states in one spin channel, basically filled, so half filled overall. And you can see this in the projected densities of states as well. And the L2 over L1 controls this crystal field splitting. So you can see here the band gap is controlled by L2 over L1, and you distort it enough, you can actually close it, but it's pretty large distortion. So we can also have further lattice symmetry reductions. What that would have as an effect is the breaking of the remaining degeneracy. So we can take these materials with trigonal symmetry and have them have point group symmetry C2H. So you have two inequivalent directions in both cases. So why is that interesting? Well, suppose you have a material that's D9, and suppose you have this strong orbital polarization. What will the state, what will the electronics look like? Well, we can just simulate this. We can take copper chloride, but rather than relax it, we can simulate it with a niobium iodine lattice structure, which has this point group symmetry. And the result is that you get this orbital polarization, which is not that strong in this case because of the very small energy differences between the P and the D states. But it illustrates this principle that you can have the strong orbital polarization and 1D conducting chains as a result. Okay, so using this knowledge, we know that there are many possible ordered insulating states. And it's maybe one reason why so many of these materials are insulating is it's pretty easy to have an ordered insulating state due to the intrinsic symmetry breaking. One of the things we have to address is how to obtain a Wannier basis that respects this trigonal symmetry. And it's actually a little bit tricky because if you just do a Wannierization on the bands, you will usually get something like the usual cubic EG and T2Gs. But you'll also have large off-diagonal densities of states, basically. So that's because Wannier 90 does not have a trigonal seed, though we can add one. And it will tend to lead to cubic orbitals. But rather than add the trigonal seed for the orbitals, the things we've done is we've rotated the Wannier orbitals in such a way that we obtain a diagonal orbital density matrix, which is pretty easy. So you can get states that are filled or not, as I've been showing you, rather than with off-diagonal density terms. So you get basically this. So the upper EG states are left alone, but the T2Gs, which are degenerate, are split into this A1G and EG. And the orbitals we get they do have the symmetry we expect. And this A1G orbital is always basically the first thing that strikes you about the symmetry of these orbitals. So one of the nice things is that this method works on any orbital projectors, whether Wanniers or just regular DFT plus U projectors, and on any symmetries. So this can be applied to things that are not halides or cubic, but to other materials as well. So just to recap, this work is on arXiv. The crystal field splitting is controlled by ligand-ligand bonds in these materials and interlayer distances, as well as further distortions. Interactions and magnetism lead to large band gaps and ordered states. And of course, in the future, one thing to do is to understand what spin-orbit coupling does. And there are novel potential states that may arise from reduced symmetry states beyond what I've been showing. And we also have this technical tool to rotate Wannier Hamiltonians to diagonalize the density matrix, which can be applied to other materials as well. So thank you for joining my talk, and please contact me if you have any questions. Thank you.